Okay, let's go to diffraction.
Okay.
That's the syllabus. Cambridge A-level syllabus. First, know the definition. Diffraction is spreading a wave front into geometrical shadow as it passes through a slit. Right? We can call it slit, we can call it gap, or we can call it aperture. So that's an obstacle. This is two obstacle if you like. Right? That's the aperture. Right? That's the aperture. We call A, size of aperture. So that is where it will go. Right? The plane wave will be deflected into the region of shadow here.
So it wants to reach that shadow, right? That's why it like diffracts.
It spread out into the region of shadow, if you like.
Okay.
Sorry, just have a bit of problem here. Right? This is the region of shadow. If I can reverse that for you. That's the region of shadow. Right? We imagine that the light is traveling in a straight line. So that is your wall, if you like. And this will be your shadow, this region of shadow. So when you have your plane wave, it spread out into the region of shadow. So if it's an experiment, we can use a ripple tank. Where this one move, vibrate up and down, produce your plane wave, and this is your aperture, right? A gap between two barrier or two obstacle. Okay, you are required to know wide gap, where your aperture size is very much greater than the wavelength. Right? So that is your gap. So suppose this is the region of shadow, right, behind the optical. You should be able to draw that. Right? Just still parallel, right? Still plane wave, but spreading out. Right? It bend. Right? This one plane wave bend away, slightly away. There's a slide only. Wavelength is still the same. Speed still the same. Doesn't change. Right? Must be able to draw. And then for narrow gap, which is almost equal to the wavelength. Sorry. Just become a mistake. Right? There's a plane wave. So come out is circular wave.
Okay.
Right? Narrow can be visualized, or you can think of it as a point source of wave. Get the size of the wavelength. So emerging wave spread out, right, into almost a semicircle. Speed doesn't change, wavelength doesn't change. Right? So you are required to differentiate only between small gap and large gap. If it is the same as the wavelength, then it will be semicircle. Wavelength of incident and reflected wave are the same. Sorry. I'm forgetting to highlight. Yep.
What happens if the aperture, right? It's much smaller than the wavelength.
Usually we won't go into that detail lah. It's a bit
Okay.
confusing when we come to smaller, that is it treat as a same as a small gap.
Okay.
Usually it's almost the same as aperture lah, or very much larger than aperture. These are the two cases we are interested in. Okay, the amount of diffraction or the amount of spreading depends on the aperture size, that size there. Right? Plane wave, circular, narrow gap, circular wave here. Why am I always so careless one? Smaller the aperture, the greater is the diffraction. Right? Or if we use optical, the same thing. Right? Longer wavelength will be better in terms of diffraction. Shorter wavelength, right? Less diffraction. Diffraction means spreading out. Right? This is the region of shadow. Right? So transmission of television signal, this is the red shadow of the hue. Right? If you use radio wave have longer wavelength. So television wave has shorter wavelength compared to radio wave. So longer wavelength for radio wave, right? Bend or diffract more than shorter wavelength. That's the application part. Right? Hardly any spreading. So this part, the house cannot receive any television wave or signal. This one can receive the radio signal. Right? You can use your pen light laser, and this is your single slit. Right? That's what we will observe. We are interested in the center one only. The two side one, less intense. Right? The intensity is here at the center one. Diffraction is on the horizontal side. Vertical is the large aperture. So that vertical is the large aperture. So no diffraction on this side. Diffraction is horizontally this side. Diffraction is on this place there. I will use circular aperture. That's why you see diffraction through a circular aperture. Right, 84% of the intensity is here. The rest will be here. More than that, we are not interested in it because the intensity is too low.
Okay.
Right? So we call that concentric ring because the center is the center of the circle.
Yes.
Smaller this gap, the greater will be this diameter. This is just for your info lah. Right? We will probably use that only in A2 lah. Other than AS, we're not interested in that. Okay, so we are interested in this one, that's all. This is just a different diagram. We can use pen light laser, single slit. Okay. Not interested in all that. Not interested in that. Not interested in that. Not interested in that. Okay. Interference of two source interference. Right? That's the syllabus. Won't worry about all this. What is interference? Where two or more waves meet at a point, there is a change in overall intensity or displacement. Okay, this is a principle of superposition. Interference tell us what do we observe. Superposition tell us how do we add up to get the resultant waveform. Okay with that so far? Superposition tell us how to add the waves. Interference tell us what we see when the wave cross.
Okay.
Coherent is a constant phase difference between the wave. Right? That's a definition you must remember. Remember what is interference. Remember what is coherent. right? So where they are same phase difference means they must be the same wavelength or same frequency. That's why it means like coherent. Coherent waves are locked together both in space and time. Space and time, same maximum at the same time, minimum at the same time. That's why it means are locked in space and time. Incoherent have no relationship to each other. It can be maximum and maximum and maximum, minimum and maximum with some other parts. They don't start at the same point in the time and space, nor do they have the same wavelength. Right? They don't have to start at the same point. Like this one, this one start at the same point, but maximum is different time, right? Different color, so they are incoherent. Different wavelength. This one is different wavelength. Right? Remember, they are going to be on top of each other if they are going to interfere. Right? They may be coherent here, but after some distance, they will be different already. Cross and cross doesn't meet anymore, so it's incoherent. Two waves are monochromatic, means not of. Right? If they are not two waves are monochromatic, means not of identical wavelength. Right? They have single wavelength but different wavelength. They will not remain coherent. They must be the same wavelength, then they can be coherent. And they can be same wavelength, but different direction, so it also won't be coherent. But in this case, they may be coherent here, but after that, you can see they are slightly out already. Maximum, not the maximum anymore.
Okay.
Right? Condition for interference. Both waves must be of same type, sound wave and sound wave, light wave and light wave. Meet at a point. They must meet at a point before they can interfere. Same direction of polarization. That means vibration in the same plane lah. Condition for wave to interfere, principle of superposition. When two waves, that you must remember. Right? Superposition, when two or more waves meet, the resultant displacement is the sum of the individual displacement. Right? That's where you add it up. Displacement. Both must be of the same type. I'm just repeating. Sound wave and sound wave meet at a point or meet at in the same region, same direction of polarization. This one different type of polarization already. One is vertical, one is horizontal, so they will interfere. Okay, 2-point interference. That's your source 1, S1. That's your source 2, S2, S1 and S2. Right? Nodal lines where cancellation occur. Right? Usually in exam, they will draw for you the crust only. And then the trough won't draw for you. You have to imagine that the trough is lighter color line, lighter color semicircle. Right? That is a crust. Sorry, that's a crust. That's the trough in between the two crusts. So this line there, AB, or sorry, nodal lines are cancellation occur. That means the crust will meet the trough here. Crust meet the trough. Crust meet the trough. So CB or CD. And the other one will be here, GH. AB is a perpendicular bisector. This one. These are your two sources, or you can redraw that as a two source. AB, that's your B here, the point there. So it means that along this perpendicular bisector, any point from S1 and S2, these two are equidistant away. Stop me if I'm going too fast, or you got question to ask. Okay or not?
Yeah, I'm fine.
Antinodal lines are lines where the reinforcement of waves occur. Example AB, reinforcement. Crust meet crust. cross, mid cross. That's another one. Or this one. Right, trough, mid trough, or cross, mid cross. That's your FG. Right, EF also the same. No antinodal line. Usually only the cross is drawn for you. The trough is not. You have to imagine the trough is in between there. Right, path different.
Sorry? Okay, fast.
Path different between S1T and S2T. This is your S1. That's your S2. Right, your T is here. So we are interested in that path different. That different in length. What's the path different? Can
I think it's 0, right?
from here to here is one wavelength, two wavelength. This one is from there to there, one wavelength, two wavelength, three wavelength, four wavelength. So the path difference is 2 lambda. Can so where the path difference is a whole wavelength is constructive interference. Right? Or you can see from the diagram. Usually we won't bother to draw all these circles, like take too long time. We calculate the path difference easier. Right? And then we put a screen there to get our observation. Okay, it's a path difference between S1Q and S2Q. That's your Q. That's your S1. That's your S2. That's the path difference. And just count it. From here to here is 1, 2, 3. That's half here. For the
3 and
right?
3 and a
this
half lambda.
S2Q. Right? That's your,
4.
okay, let's see. S2Q is 5 lambda minus 3.5. So it's 1.5. So 1.5 is destructive interference. Wherever you have a half, it's destructive interference. Have a go at S2P and S1P. Sorry, a bit difficult because I didn't send you the worksheet.
Okay, okay.
Can?
Sorry?
Can or not the answer?
Can.
So you should get 2 lambda. So it'll be constructive interference. Okay.
Yes.
So normally we won't draw all this diagram lah. We just use a path difference, the extra distance which a wave travel compared to the other one. So if it's whole number, right, 0, 1, 2, 3, or 0, lambda, 2 lambda, 3 lambda, that is constructive interference. If it's half lambda, 3.5, 1.5, or 2.5, or we can summarize it as that 2m minus 1, close bracket, half lambda, m is 1, 2, and 3. Remember m, right? That is your 0. Half lambda doesn't start with 0, it starts with 1, right? Half lambda, right? You can put it in there. 1 is 2 minus 1 is half lambda. Okay.
Yep.
Okay, you can write in the, there's the alternative form to write. Yeah, it's alternative form, same thing. I just multiply by 2, that's all. Okay, for path difference 0, they are exactly the same length. So we call that your m equals to 0. And then that's the bright fringe. That's the center one. Sorry, this is the center one. This is the first one. This is the second one. Second bright fringe. So the path difference, the distance, that distance there is 2 lambda. Right? Between the two waveform. Right? Sometimes people will use m, sometimes will use n. Doesn't depend on the textbook, doesn't matter. M equals to 0 is the 0th order of the central bright fringe. If you use like M1 is the first order, first bright fringe. That's the name given. Right, this one just sure. I think we won't bother about all that. Right? We can use 1 point if we want to show spreading of the wave, spherical waves, and then interference of 2-point source using a ripple tank. Right? You can use microwave. This is your detector. This is your transmitter. Okay, microwave. There's a frequency about 10,000 megahertz. Okay, you need to remember microwave, roughly the wavelength. Right? That's the transmitter. This is the detector. That's the metal sheet. Metal reflects completely microwave. Cardboard reflects partially. That's why we use metal. Right? So A, the aperture size is about 3 cm. The distance between the aperture is about 6 cm. Okay, these are the same thing. Just different way of drawing the thing. Okay, lamp is not a coherent light source. You can get from internet, but be careful. Right? The lamp has to be monochromatic source. Lamp is a white light source.
Okay.
Right? It gives out more than one light. So lamp cannot use a lamp to produce circular wave. Need a single slit. Okay. So microwave, you need to remember either the wavelength or the frequency, and then the size is about 3 cm, the aperture size. Distance between the aperture is 6 cm. Right? Transmitter is the one that emits microwave, and the two wave train will come out from the double slit and the detector. Right? Is moved along a line perpendicular to the center. You can move along the straight line or circular line if you like. Receiver or detector detects the maxima or minima of the intensity and are shown as high or low. Right? There's a meter to show you high voltage, high voltage or low voltage, or low current, high current. What's the requirement? Condition for interference must be coherent. Same frequency, same speed, same amplitude. For light, you need another same type and plane of polarization as for light. Young double slit experiment, we are using narrow slit. Screen slit distance large. Okay, that's the setup. Single slit and double slit, yes. These two are parallel. These two slits, single slit, double slit, are parallel to each other and perpendicular to the light source. So what we observe, bright and dark band evenly spaced. Right, that's your D. Distance between the slits, I call it small d lah. Right, consistent with your diffraction grating, but I think your textbook use it as A lah. Okay, doesn't matter. It's A or D only. And then I call that Y. You can call it X if you want to. Okay, sodium lamp. So Y is the yellow light. And then it's diffracted by a single slit. And then the single slit, they are from the same wavefront. They interfere in this region of interference, this one. This is a diffraction from S1, this one. This is a diffraction of S2. So that's the region of interference. That means you can only find the bright and dark band in this region only, not outside here. Outside here is no more interference. Okay, we interfere in this region. Okay, so if it's vertical slit, then vertical bright band. Characteristic of interference fringes or bands. Observation, alternate bright and dark. Evenly spaced fringes are observed on the screen. Number of fringes or bands depend on the amount of diffraction occurring at the slits, and this depends on the aperture size or the width of the aperture. Fringes are found only in the region of overlap. Okay, are you all right, Brian? Ryan?
Sorry, the internet connection was bad.
Okay, any questions so far?
No, no so far.
Okay, we are short of time already, so we are going to stop in 10 minutes time. Right, there is the region of interference. Right, this is the diffraction from the single slit. This wide aperture, this narrow aperture. So this is the region of interference where you will find the fringes here. And then memorize the formula. Either this is X or Y. That is D or small a. Doesn't matter, but memorize the formula. Yeah.
How do you derive the formula?
Let me see whether you need to derive or not. Always go to the syllabus. If it's not required to derive, then no need to recall only. Recall and use. No derive. Don't waste your time. You don't have much time already. Where did we stop? Okay, we stopped here the previously. Right? This is for white slit, narrow region of interference. That means the number of fringes will be very few. Right? This one will be more fringes here, you'll see. Right? Narrow gap. Right? That's the intensity distance graph, or I can call it d sine theta. Right? For distance x. Threshold of vision, that means our eye can only see to a certain level of light intensity. If the intensity is low, we cannot see anymore. We treat it as dark already. That's why we see not a dark line, but a dark band. Intensity of each band is the same. Right? That's why this graph is showing you. Threshold of human vision causes the annulment. Annulment means cancellation position to appear as the dark fringes rather than the dark line. Right? This one we look at a plane view. Right? Remember the single slit is the size of the wavelength. Right? It diffracts, that's the diffraction. And this is monochromatic light. And then from the same wavefront, this is your point source, this is a point. That's how we make it coherent. They are from the same wavefront. The wave leaving the double slits are from the same wavefront. So they are coherent. Coherent wave leaving the double slits are diffracted. Right? This one a little bit confusing. The two waveform from two different slits interfere. That's how we get our bright, dark, bright. Okay, this one just trying to show you also the same thing. Usually we need a lens. Right? There's your monochromatic source. There's your lens. There's your focal length there to get your plane wave coming to the single slit. Okay, so you must know the path difference. Not path difference. These two are the same length. Path difference 0. Right? This one, the first dark band, is where the path difference is half lambda. That means this one has to travel a longer distance than this one by a half lambda. So this will be destructive interference. This will be constructive interference. Right? This is just to show you path difference, that's all. Right? Constructive here. This is the first one. Constructive. Path difference lambda. That's destructive. Half a path difference half lambda. Right? That's the path difference. That's what it means by path difference. Right? The extra length that you have to travel. So this part give you the displacement distance graph. This part will give you your observation on the screen, give you the displacement time graph. Right? So that is your central bright fringe. Path difference is 0. First bright band, path difference is lambda. Okay, this one show you the same thing, summarize the same thing. Path difference is 0, half lambda on two sides. And then the first bright band, the first bright band after that is called your lambda, path difference is lambda. Okay, this one is just expressing you can get from internet. Right? But you should be able to identify the path difference is 0, path difference lambda, path difference is half lambda. Okay, so if that is the center bright fringe, then you should be able to label this 0, 1, 2, 3. Path difference is 0, lambda, 2 lambda, 3 lambda. Right? General equation, n lambda, n is 0, 1, 2, 3, and so on. Dark fringe, Right? That's the first one. There's the second one. There's the third one. Or the path difference is half lambda. That is your 1.5. This is 2.5 lambda. Right? This one. Okay, should be able to identify them. Okay, or the general equation. Okay, I will download into the YouTube. You can download in YouTube. Got problem? Let me know.
Okay.
So that you don't have to store in your computer. Okay, same as what we just now draw. Right? All we need to do is we just put a screen there, and then that's what we see. Bright, bright, bright. Okay, just relate it to what we studied previously. Okay, RS are point sources of light. P is on the screen. R and S are in phase. Intensity at P is 0. So question, if R and S are 180 degrees out of phase, what is the intensity at P? What's your answer? Okay, I think I'll let it, you can, it will be maximum because there is a, this is a path difference of half lambda. So another path difference of half lambda will make it constructed interference at P. Okay, our time is running out, so I have to go very fast.
Okay. Sure.
Okay. You won't bother about deriving it. Right? Know the parameters that they stand for. Right? Memorize this formula. It will summarize for you the effect of changing D, effect of changing small d, effect of changing lambda, or sometimes they will say frequency. And then know the roughly the magnitude. Right? The D, that distance there is about 0.5 millimeter. That distance there is 2 meter. Right? If it's cut off, it's okay. Right? We are going to cut off soon. So the aperture size is about 0.1. Right? You can see very much greater than the wavelength. Y is on the screen here. Right? I don't think we want to go any further. Just remember these two formula. This one intensity. The further the distance, the smaller is the intensity. That means the smaller is the amplitude of the wave. Okay, I will stop here. Let me know if you still need help. I will stop here.
Okay.
Our time is up already anyway.